So let me a recap from last time. I tried to define this object, the classifying space of Haefliger spaces, and tell you why we should care about them. So let me quickly recall what the definition was and what the motivation was. So remember, when we wanted to think about foliations, we cover the manifold by some open covers, and on each of these open sets, we have maps to say Rk, maybe F alpha and F beta, and then these are going to be open sets in Rk, and then to actually get some sort of structure, we want to have transition functions that are local diffeomorphisms in Rk. So this is what the direction is. So F beta is alpha. Okay, so this is. And we said that the data of the cover, the maps F alpha, and the transition functions, it gives us what we call Haefliger structure. And if these maps, say F alphas, were submersions, then it actually gives us genuine foliation. If not, it's going to be something singular that we can regularize later. Okay, and then we define this groupoid gamma k, whose objects were points in Rk, and morphisms were given by germs. And so let me again recall what the main players are. So the classifying space of this groupoid, we denoted by B gamma. We said that in the case of smooth category, it has a map to BGLK, and the fiber of this map is denoted by B gamma K bar. And similarly, if you have group G, so let G be a topological group, then we have a map from BG delta, and this is discrete with discrete topology, to BG. This is a map that is induced on the level of groups by just identity. It goes from G as an abstract group to G as a topological group with identity homomorphism. So it induces a map on classifying spaces. Geometrically, the way you should think about this is that this is classifying G bundles for you, and this is classifying flat G bundles for you. And the fiber of this is called BG bar. And the content of Mather Thurston was that one could relate this object to the B gamma K bar. So let me recall some results in this direction. So last time, one thing I said was that perfectness of say the H1 of, so this is a group homology. So one can write this as B of, say, def compactly supported R discrete. If I decorate this with R, I mean CR diffeomorphisms. This is isomorphic to H2 of B gamma 1 R bar. And this is the same as pi 2 of B gamma 1 R bar. And we said that, oh, this is just related to perfectness, and perfectness of this is related to the connectivity. Okay? And so one theorem due to Thurston was that the B gamma K infinity, or C infinity, bar is at least K plus 1 connected. So the homotopy groups up to K plus 1 vanish. And the K plus first homotopy group is the one that is related to the perfectness of diffeomorphism groups in dimension K. And important conjecture is that this space is actually 2K connected. So still very open. So B gamma K bar, in fact, in any regularity is 2K connected. Okay, and let me mention a few things that are known in this direction. So one is, in fact, it's known by Mather that B gamma K 0, C0 regularity, this is contractible. This is basically due to Mather. And one remarkable theorem of Suboy is that the C1 version is also true. So B gamma K 1 bar is also contractible. And I'm going to tell you the idea for C0. In case you haven't seen it, it's known, it goes under Mather's trick. Which is very useful. So let me just say the following. So I guess proposition, compactly supported homeomorphisms of Rn as a group. In fact, Mather showed that it's a cyclic group. Okay, but let's see that it's actually perfect and uniformly perfect. Okay, the idea is the same. So being perfect means that H1 is 0, which means that anything is in a commutator subgroup. And the same idea is going to do the higher group homology. So if you have some element F here that you want to write as a commutator, the support of F is enclosed in some big ball, maybe. So suppose that this is this contains the support of F. Okay. Then you find some, again, compactly supported homeomorphism of G that is going to displace this support and make it smaller. Until maybe you converge to a point in Rn. Okay? There exists such G that does this, and then you define a new element here that, let me see. So you can make sense of, say, H to be the infinite product of, F, maybe G inverse G, Gi, or I. Okay? And this makes sense, although it's infinite product, say from 0 to infinity. It's going to be, so this element is going to be compactly supported homeomorphism of Rn. It's okay? And now you can write F as a commutator using G. So how? So you see, if you take the say G H G inverse and then multiplied by F, this is like H. So then you can write F as whatever. So it's going to be H G H inverse G inverse. With the other way around? Okay. So in fact, you can write any element as just one commutator. So this idea can be souped up to prove that it's acyclic. And Suboi does the same thing in C1, and you see that the same thing doesn't do the job when you have regularity, because this is not going to make sense if you want to think about derivative. You have to do it in a very dynamically genius fashion. And then you use this and Mather's theorem to prove contractibility of that space that we are interested in. And as I emphasized last time, this is opposite to the philosophy of H principle. Somehow we are using diffeomorphism group or homeomorphism group that are geometrically more rigid objects to prove something interesting about this B gamma that is more flexible object. One thing that happens already in the smooth category that has the right flavor in the direction of the H principle that I advocated last time is done when you think about non-compactly supported things. Okay, so here is another theorem by Graham-Siegel that he proved that if you consider, say, entire diffeomorphism group, it doesn't matter what regularity, say R, Rn, as a discrete group, and take the classifying space, it maps to B gamma and R. And geometrically, this is the classifying space for foliated Rn bundles, and this is the classifying space for Haefliger codimension n. And Siegel says that this is homology isomorphism. Okay, this is also a very non-trivial statement, but it's a very homotopy theoretic statement. This space is not simply connected, and it tells you that if you do the so-called plus construction, you get this. Okay, and basically he's only using the fact that you have dilations and you have isotopy extension. So whatever group you use here that has such properties, you're going to easily prove such statement using Siegel's technique. And this statement already tells you that def of Rn isotopic to identity is a perfect group. And that's a very non-trivial statement group theoretically. Okay, so this implies that def of Rn isotopic to identity is perfect. Note that this is a kind of a group that, last time I said, for many of these groups, perfectness implies simplicity. This is only perfect and not simple. This has non-trivial normal subgroup, in particular compactly supported ones, is a normal subgroup. But it's a perfect group. And this is a kind of a statement that I'm trying to get at. One can actually prove that this is perfect using dynamical techniques, and people have done this. Maybe I should give credits to Ling, Schweitzer, MacDuff. These people gave a dynamical proof of the perfectness in the non-compactly supported setting, but I think this is the right direction here, concluding something about diff using B gamma. And the reason is that now we know that pi1 of B gamma is 0, so you get perfectness here. Yep.
Is it known if it's uniformly perfect?
It is uniformly perfect. Yes. Yes. There is no. It is uniformly perfect, but it's easier to show that there is no quasi-morphism. But it's harder to.
Question: isn't there any problem when R is n+1?
Oh, that's a good question. No, this is actually the interesting thing when you work with non-compactly supported diffeomorphism. So let me actually give a remark. As Michele just said, here is an important open question that it is not known that diff R compactly supported isotopic to identity Rn is perfect when R regularity is n+1. It's known to be perfect, or in fact simple, for any other regularity. But this regularity is special. And it's a very important, I guess, open question for people who are interested in, dynamics of these things. I mean, in particular, C2 diffeomorphisms of circle, it's not known to be simple group. That's a very famous open problem. But when you forget about the compactly supported things, there is no restriction on regularity. This is true for all regularities. Yeah. Okay. What else? Oh, I wanted to say something about PL. So last time I mentioned that one theorem was that that actually goes back to Greenberg. Tells you that B gamma 1 PL has certain homotopy type. You can completely understand it. BR. And joint of two connected spaces is known to be at least two connected. Okay? So this already tells you that just the fact that it's a joint, it already tells you that pi1 and pi2 are 0. And vanishing of pi2 of B gamma 1, as I mentioned above, it's equivalent to the perfectness of PL. But the perfectness in dimension 1 was easy. But this is a homotopy theoretic proof of that easy theorem. That's not, I guess, the advantage of using homotopy theory. But in codimension, in dimension 2, I said that B gamma 2 PL bar is 4 connected. And this implies that PL compactly supported R2, or in fact for any surface, isotopic to identity. This is connected, so there is no reason to say isotopic to identity is perfect or simple. And simplicity here means something, tells you something about the structure of this group. So here is one thing that I want to mention, so this goes back to Epstein, that asks this question about the algebraic properties of these groups. So he defined what he called glide homeomorphisms. And glide homeomorphism is, say in dimension 2, you can guess what it is in higher dimensions. So you know what is the PL homeomorphism of an interval. And then you can, from the PL homeomorphism of interval, you can define certain PL homeomorphisms of disk, D2. And the way you do it, you just take the join of the interval and 2 points. So this is going to give you the 2 disk. And then you just take the cone of the PL homeomorphisms at each level. Okay? And because this is in a commutator subgroup, what you get in a PL of D2 is also going to be in a commutator subgroup of the disk. Okay? And then his conjecture is that PL homomorphism in any dimension is generated by glide homomorphisms. Okay? And if you can show that, then you can prove that PL homomorphism isotopic to identity is in fact a perfect group. In dimension 2, this simplicity result already tells you that PL homomorphism of the plane is generated by glides. Okay, so I guess as a corollary, PL homomorphisms of the plane is generated by glides. Okay. But again, this is a very non-constructive way of doing this. Let me tell you a little bit about some similarities.
Wait, what do you mean by that? You're also considering conjugates of glide?
Yes, anything that, yes.
Okay.
Right. Yeah.
More tricks for PL than there are for smooth? There's fewer tricks, right?
Sorry, say that again.
Are there new tricks used for calculating the PL case? I mean, you've got glides, and you have the Mather slide, but what other tricks are in the toolbox?
I mean, when I said this, I used the version of Mather Thurston for PL and Greenberg, basically.
Greenberg have new tricks?
Greenberg tells you how to study the homotopy type of B-gamma PL, which I'm going to talk about. And then you just do calculations, basically, with that model. Okay, so few comparisons between PL and diff that, the techniques that one, as Steve was asking, so the techniques that one can use for diff, some of the techniques are dynamical that doesn't apply for PL, but they have some properties that are very similar. So for example, there is a theorem that is called Thurston stability. So Thurston stability I'm not going to tell you what it says. It's about stability of leaves of foliations that are at least C1. But it has an interesting consequence for diffeomorphism group. For example, in dimension 2, if you consider diffeomorphism group of a disk, say D2 rel boundary, well, this is an interesting group, right? At least C1. Thurston tells you that this group is, Thurston stability, which is purely foliation theoretic, tells you that this group is locally indicable. The thing that Yash defined this morning. So it's a locally indicable group. And again, what it means is that any finitely generated subgroup of it has surjection to Z. In particular, any finitely generated subgroup is not perfect. The group is perfect, but any finitely generated subgroup is not going to be perfect. Okay? So that's one property. And the same statement holds for PL. So this is a theorem of Caligari and Rolfson that says that PL of D2 real boundary is locally indicable. Again, if you consider rel being near the boundary, then what I said says that it's actually a simple group. And Caligari-Rolfson theorem tells you that it's a locally indicable group. So again, very similar. If you relax the regularity to C0, it's not true. Okay, so remark, I think it's a theorem of height, but correct me if I'm not correct. It's true. Okay, so homeomorphism of D2 rel boundary. I think he showed that it's not left orderable. Remember, we said that locally indicable implies left orderability, and he showed that it's not left orderable. Okay, so it's kind of sensitive to regularity, and in this way, PL and diff behave in the same way. But last time I said that there are some differences. So in dimension 1, there was this class God-belong way. So the God-belong way in diff is a class that lives in degree 2 of diffeomorphism group of the circle, which is non-trivial. Okay. So this is a class that gives you interesting central extension that Hyun-Kyu was interested in, and the question, one interesting question that that Takashi is talking about is that, if you know, there's an Euler class here and there's a God-belong class, and somehow it's a very open question that whether that's all. Okay, so if something has a vanishing God-belong can we show that it's actually null-bordant? So that's a hard geometric question. And the same thing also exists in PL. So there is this G star Giesco GV, again non-trivial in H2 of PL. And in dimension 2, if you go up in dimension, there exist again God-belong classes. So they go by the name of H1C1 squared and H1C2. Or I should say, integration along the fibers. Don't worry about these things. These are classes in H3. Goodness, H3 of, say, def at least C2 of, say, D2 real boundary. But the theorem that I mentioned last time says that H3 of PL D2 real boundary, at least with Q coefficients, is 0. Okay, so in dimension 2, we will see we'll see some difference, okay, between diff and PL. And another, I think, interesting difference is what goes under, those who are interested in characteristic classes goes under Bott vanishing. Bott vanishing tells you that, if you have a manifold M, say, of dimension n, and a foliation, say, of dimension k, you can look at the normal bundle of the foliation, and this is k-dimensional vector bundle, and it's got some characteristic classes, okay? And it tells you that if you look at the Pontryagin monomials of degree bigger than 2k, it's going to be 0 rationally. So, for example, in codimension 1, when you have a circle bundle, you have Euler class, and Euler class squared is given by the first Pontryagin class. And if you think about the condition on the codimension, it tells you that the Bott vanishing implies that when you think about the Euler class in H2 of the diff of S1, say at least C2, it tells you that e to the power 4 is going to be 0. It's a consequence of Bott vanishing. Okay? It's not known whether e to the power 3 is 0, but it's known that e to the power 4 is 0. Sorry, I should say I'm gonna change this a little bit. Let me say H2 in B gamma 2 C2 R bigger than 2. I shouldn't formulate it in the case of circle. When you have a codimension 2 smooth foliation, you get a vector bundle, and it's got an Euler class, and then e to the power 4 is going to be 0. And the same thing is not true in a PL case. So that's so Bott vanishing does not hold. Bott vanishing does not hold in a PL case.
Sam?
Yes?
This guy called Morita, right? He showed that he got these classes with the mapping class group by looking at Bott vanishing. He got his higher characteristic classes for the mapping class group.
Okay.
Does that mean that they don't exist for the PL mapping class group? Instead of homeo, you look at PL on the surface? And so does that mean that that whole Morita program doesn't work PL?
I don't exactly know what classes you're mentioning
Well, when you
that
look
are.
at the powers of Euler and integrate over the fiber.
Oh, they do exist and they're non-trivial.
They don't, but you don't have the vanishing. So you don't, right?
Right.
So is the PL case of the mapping class group different?
It's
That makes sense.
it's different in the sense of you don't have vanishing, yes, but they exist.
Oh,
Yes. Yes, you're right. So these MMM classes, when you work with the smooth diffeomorphism of the surfaces, they're going to vanish as you go up in dimension, but they're not going to vanish in PL.
so it's a different theory for PL.
In the sense of characteristic classes, yes. So in particular, I shouldn't take too much time for this. You see, if you consider B, def of Rn discrete to B diff of Rn. This is homotopically BGLN, so this is a comment for those who are interested, I guess, in characteristic classes. There is also BPLN, R, discrete, and BPLN. And, well, BGLN maps here. So bot vanishing tells you that if you look at the Pontryagin classes here and pull them back here, they're going to vanish in higher degrees. In the case of PL, one can also make sense of PL Pontryagin classes. And the non-existence of bot vanishing tells you that when you pull them back to the discrete version, they're non-zero. So in particular, there is a story about combinatorial formula for Pontryagin classes that is going to be a theory about this. But when you pull them back, it actually tells you that you should be able to find a natural group co-cycle for them. So there should be a way of saying, what is a nice co-cycle representative of Pontryagin classes on PL and R.
That's not been done, right?
That I don't know.
That's what it's called.
Right. Okay. That was supposed to be a recap, but it took too much time. So let me now actually talk about B gamma 1 PL by Greenberg. Okay. So I have to define some notions that Greenberg is using. So now I want to talk about Greenberg's model for B gamma 1 PL. Any question before we change gears? Okay. So remember, at the beginning we said that when we think about geometry, we have some model space X, and then we think about maybe some sort of isometry of that space or some sort of pseudo transformations on that space, and then every other manifold somehow is locally modeled by that fixed model space X. For Greenberg, when he talks about geometry, and he actually uses this, so I'm going to use Greenberg's notation. So by geo, in his papers, he means basically, geo X. He means some étale groupoid. I'm going to say what that means. Over X. So étale groupoid gamma. So you think of gamma as space of morphisms, and you have source and target over a space of objects X. And étale means that S and T are local homeomorphisms. So okay, so for Greenberg, geometry means, having some étale groupoid over some interesting topological space X. So let me just say it in words. If you have, a pseudo group of transformations on X, you can get groupoid by just looking at germs of elements in the pseudo group. But this is a more general notion. Later, we are going to give this example by Greenberg that he thinks about some interesting Caesar congruence group that is given by curves in R2. And there, the groupoid, the object is one-dimensional, but the pseudo-transformations are given by those transformations on the curve that can be locally extended to the plane. And that's going to give you some interesting Caesar congruence group. Hopefully, I'm going to talk about it in the next talk. But what's the setup now? So the setup is called the simple extensions with isolated singularities. So when you think about PL, say in this talk, it's one-dimensional. You're thinking about line, basically. So PL homeomorphism has isolated singularities. And you know that away from the singularities, it's somewhat understandable. And when you think about the classifying space, you want to make sense of the regular part and the germs at the singularities. So his setup is, suppose you have some groupoid that he denotes by gamma A that is a subgroupoid of gamma with the following properties. So these are geos on some n-dimensional manifold with the following properties. So 1, 15 minutes. There exists some fixed point in X such that the gamma orbit of B is the same as the regular orbit of B. So there is a distinguished orbit of the action of these groupoids that are the same under the regular parts and the non-regular parts. That's one condition. 2, you want to make sense of this being isolated singularity. And the way you do it in this groupoid picture is as follows. So if U in X is an open set, and say G is a section of the source map, then there exists S, locally finite set such that S is in U intersection of the orbits, and And G away from this locally finite set is regular, meaning that it's in gamma A. Okay, this is basically saying that, you know, there is some distinguished orbit that these two geometries, they give the same orbit on that distinguished point. And away from some locally finite set, locally you're regular. Okay? Maybe I give 2 examples. Something that is related to Thomson group, for example, you can, maybe a bit simpler than Thomson group is as follows. You know, consider the following, you know, action of Z on R that is given by, you know, using homeomorphisms of, say, G and X given by 2 to the power nx. And the regular part is a groupoid. You know, generated by you know, restrictions of GNs to open sets. And a non-regular groupoid, the only difference is that, so gamma is as follows. So if U is in R open, say G here, then, and so if 0 is not in U, then restriction of G to U is given by Gn for some n. And if 0 is in U, then you say G of x is given by, you know, Gnx for x bigger than 0 and Gmx for x less than 0 for some mn. Okay? So you allow, you know, singularity at this point. And this is a simple extension that is related to Thomson group. And if you if you look at the classifying space of these groupoids, you get the following thing. So you see the germ of gamma A at the singular point 0 is basically the group Z. And the germ of gamma at 0 is Z times Z. Okay? So now you're thinking that, oh, the classifying space of gamma should be constructed from classifying space of the regular part and these germs, groups, Z and Z times Z. And I haven't told you what the model is, but it's going to be, so in this case, B gamma is going to be homotopy equivalent to S3. And in the case of PL, you know, when we think about PL of the line, again, here, if you think about the regular part, say at 0, it's just given by slope. So there it's R. And the germ of a non-regular part is going to be R times R. So it's very similar to this example. And then instead of S3, which is S1 joint with S1, in this case, you get B gamma 1 PL is BR joint BR. So it's actually conceptually very similar to the case of a Thomson group. If you think about S3 as S1 joint S1. And S1 is BZ. You see, this is okay, so let me yes.
So your x in this example is
R.
And what is how do you get these maps S and T?
Oh, the source and target maps?
Yes.
So it's given by, you know, germs of, you know, homomorphisms, local homomorphisms that are generated like that. So the S and T are just, so you look at the germs, and the S and T is the source of a germ and the target of a germ.
Which are subsets of R.
Yeah, it maps to R.
So the source is a subset of R, right?
The source is a map from the space of morphisms, which is the germs of maps that are given like that to R. Wasn't convincing. I can explain more. So let me maybe end with the model. So this is going to be, since I don't have time to define everything, let me just tell you roughly what the statement looks like and then explain it next time. So, let G be the germ of you know, gamma maps, gamma homomorphisms at B. Okay? And GA be the germ of gamma A maps at B. Okay? So B is this specific point that we look at its orbits, and you look at, you know, germ at this point. It's a group. For example, in this case, in the case of PL, when you look at the germ at 0, you get R. It's just the slope, and the germ of gamma maps is going to be R times R. Okay? So we have these two groups, and the idea is you want to say that the classifying space of gamma is constructed from B gamma A and the classifying space of these germs. But one problem is that the group of germs does not act on anything interesting somehow. It's hard to let the group of germs act on something because it's just germs. It acts on a point, but it's hard to let it act on anything interesting. One way to, so there's a way to make sense of letting it act on Rn. So it's a theorem of Greenberg. Says that you have this diagram. So let me actually not. So remember, X was n-dimensional. So X is n-dimensional. And when you look at the germ, somehow you see a neighborhood that it's like Rn. And you would like to have a model that the germ acts on Rn. Okay, it doesn't act on the nodes, but it acts in a homotopy coherent way. So one can actually make sense of, the action of G on Rn. And it acts also on Rn minus a point. This is going to be the singularity that you remove. And then there is an action of Ga, again, on Rn minus a point. There's an action of Ga on Rn. And all these things map to B gamma A. And the theorem is that the co-limit of this is B gamma. Okay? Somehow this statement might be a little bit scary, but somehow the concept is what matters, and I should convince you next time that this is computable. That when you think about B gamma that has isolated singularity, you want to build this from the regular parts and the way that germs act near that point. And this is how this is modeled, okay? But I have to say what these spaces are. So this action is like an Rn bundle over Bg. This is like sphere bundle over Bg, and so on. So topologically, this is like the classifying space of the germ G, and this is like a sphere bundle. Okay, we're going to talk more about this next time. Thank you.
So that's Greenberg's new construction, this idea of how to build a local model?
Right, that's actually only dimension 1 in a way. And then if we get to it in the next talk, he has some inductive way of thinking about this that is actually very interesting. And the piecewise projective naturally shows up there. Because you want to think about piecewise linear homeomorphisms of, say, R2. Their singularity is not isolated. It's given by, it's stratified. It could be a point, it could be a line, it could be, some bunch of lines and so on. And then you want to build an inductive model by this stratification of the singularity to build the B gamma 2PL and so on. But this proves the B gamma 1 PL case. I'm going to say how the induction works next time.
So, sorry, I didn't get in your last theorem how G is related to gamma.
G is so gamma is a groupoid. G is a group. And G is the group that you get by restricting the gamma maps to just the point B. For example, in the case of piecewise linear homomorphism of a line, say you look at the origin and you restrict PL homomorphism near the origin, you're either given by a real number or two real numbers. So it's isomorphic to R times R. Yes?
So earlier you mentioned the bot vanishing. Is there such a thing as bot vanishing for Haefliger structures?
Yes.
And then that's what you use later?
Yes, that fails in PL.
But for
a smooth,
ordinary or smooth
yes.
Haefliger structure. It's interesting. Is there a partial connection on the normal bundle?
The so-called bot connection, yes. When you have smooth, but not PL.
No, I understand. That's somewhat surprising. I just thought that this flat partial connection is well, it's flat because there's a tangent model to the leaves.
Right.
But in Haefliger structures, there's no tangent.
Right.
And nonetheless, okay.
Right. Right. All right. Well, if there's no more question, I guess we will resume 15 minutes for